Hello friends, welcome back to my YouTube channel. In this lecture, I will discuss step-by-step procedure on how to design a laterally supported beam using IS 800-2007 code. So please stay tuned as this kind of content is not available on any other YouTube channel. So first of all, what is a laterally supported beam? From the name itself, we can say that a beam that is supported laterally through any kind of restraint is called as laterally supported beam. But why are we restraining it? And the answer is simple. In order to prevent lateral torsional buckling. So guys, if you have not seen my previous video on lateral torsional buckling, you can watch it. I will attach the link in the description below. Now, how to restrict the beam's lateral movement? So there are many ways in order to restrain the beam laterally. In the figure you can see the beam is fully encased in concrete. So this will restrict the movement in the lateral direction. In the second figure, you can see that we are using the friction between the steel and concrete to prevent the lateral movement. In the third figure, you can see that the steel beam is connected using shear studs to the concrete to restrict the lateral movement. And the fourth method, which is the most common method, is the use of the plan bracings. So plan bracings is connected near the top flange, and this will restrict the movement of the top flange laterally and prevent lateral torsional buckling. Now, before proceeding with the design, first of all we need to understand the section classification that is given in IS 800-2007. So as per the code, there are four types of sections. First is a plastic section. So a plastic section is a section in which full plastic hinge will develop, and that hinge can undergo unlimited rotations by the formation of plastic mechanism. The next section is a compact section. So this section can develop plastic movement resistance, but it will be unable to develop the plastic hinge that is required for the formation of plastic mechanism. The third one is the semi-compact section. So here this section will not even reach the plastic capacity. It will just reach the yield stress, and it will be unable to reach the plastic moment of resistance, and it will yield due to local buckling. And the fourth one is a slender section. So this section will not even reach the yield stress. So as per the code, these sections are prohibited for use practically. Okay, so I have compared all these sections through a graph. As you can see, the plastic section is also called as the class 1 section. So in this section, we will have full plastic moment resistance developed, and this plastic moment resistance will also help in the formation of plastic mechanism. So when the plastic mechanism is formed, you can see that there will be very high rotation that is allowed for the plastic section. Compact section, you can see that it will reach the plastic moment MP, as you can see here in the graph, but it will not form a plastic mechanism. Okay, the third one is a semi-compact section, or it is also called as a class C section. Here you can see that it will reach the yield moment, but it will not reach the plastic moment. And the fourth one is a slender section, or the class 4 section, and this section will not also even reach the yield moment itself. Okay, now how can we classify the sections? So in order to classify a section, we need to use table 2 of IS 800-2007. So let me show that table to you. So as you can see, there is a table given in IS 800 2007. So we need to classify the different elements. So first of all, let's check the flange. So for the flange, let's say our section is a rolled section. Okay. So we need to see the ratio of B by TF. Okay. What is B and what is TF? That is given over here. Okay. For different type of shapes like I section, channel section, angle section. What is the value of D? What is the value of B? So here you can see that B is nothing but half of the flange width for the case of I section. Okay. What is TF? TF is nothing but the thickness of the flange. Okay. So once we have the ratio of B by TF, if this ratio is less than 9.4 times of E. Now what is E? E is square root of 250 divided by Fy. So generally Fy is 250. So square root of 250 by 250 is 1. So if my value of B by TF is less than 9.4 into 1, E is 1. So if it is less than 9.4, then we will classify the section as plastic. If it is in between 9.4 and 10.5, means if it is less than 10.5, then we will classify it as compact. And if it is less than 15.7 but more than 10.5, then we will classify it as semi-compact. Okay. And anything more than 15.7, we will classify it as slender section. In a similar manner, we will also classify the web. So once we have the web and the flange, let's say that my flange is plastic and my web is also plastic, then my full section will be plastic. But if in case my web is, let's say, slender and my flange is semi-compact, then I need to consider my section as the worst condition. So out of semi-compact and slender, the worst condition is slender. So I will consider it as slender section. Okay. So let me show this section classification with the help of an example. So here I have shown an example for ISMB 400. So for ISMB 400, the overall depth is 400 mm. Okay. Flange width is 140 mm. Flange thickness is 16 mm. Web thickness is 8.9 mm. Yield stress is 250. So E value is square root of 250 by Fi, which is 1. Okay. Where I have got all these values, you can get it from steel table. Okay. So first of all, let's classify the flange. B by TF. What is B? As I already showed you, B is nothing but half of the flange thickness in the case of I section. So flange thickness is 140, so half is 70, and thickness of flange is 16, so it is 4.375. So from the table you can see that it is less than 9.4. So we can say that it is, my flange is plastic. Okay. Similarly, we will categorize the web. So for web, we need to check the ratio of D by TW. Okay. What is D? You can again see from that figure, right? If this is my I section, okay. What is D? D is this one. Okay. So how to calculate this D? Simple, right? Overall depth minus 2 times of the flange thickness from the top and the bottom. Okay. So overall depth is 400 minus 2 into flange thickness is 16 and divided by thickness of web, it is 8.9. So it will come out as 41.35. So again you can see that it is less than 84. Okay. Let me show you these values as well. Okay. Now let's check how to calculate the design moment capacity. So in the code, there are two cases given. First of all, we need to check what is the shear force that is acting on the beam. Okay. If my shear force is less than 60% of the design shear capacity of the beam, so my design shear capacity of the beam is VD. Okay. So if my shear force that is acting on the beam is less than or equal to 0.6 times of the design shear capacity, then the code says that that kind of shear is called as the low shear. It is called as the low shear force. So in the case of low shear force, whatever the moment capacity that I will get, I will not reduce that moment capacity because my shear force is low and it will not interact with my moment. So as per the code, whatever the moment capacity that we will be calculating as per the formula, we need to use it as it is. Should not reduce that moment capacity. Okay. So how to calculate that moment capacity? So in the code it is given that the design moment capacity MD is equal to beta B ZP Fy by gamma Avo for the plastic and compact sections. Okay. And to avoid the onset of plasticity under service loads, MD is limited. So in any case, this MD should be less than 1.2 ZeFi by gamma M for the simply supported beams, and should be less than or equal to 1.5 Ze by Fi by gamma M for the cantilever beams. Okay, and for the semi-compact sections, this MD is governed by the elastic section modulus, that is Ze. Okay, in the case of plastic and compact, it is governed by the ZP, that is the plastic section modulus. Okay, so these are the formulas for calculating the design moment capacity. Okay, in the case when V is less than 0.6 of my VD. What is VD? VD is the design shear force. Okay, so first of all, we need to check whether it is low shear force or the high shear force. So, what if it is high shear force? So, my V is more than 0.6 VD. So, in this case, the code says that the design bending strength that we will be calculating, that should be reduced by a factor. Why it should be reduced by a factor? Because this is a high shear force. So if my shear force is more than 60% of the design strength, shear strength of the beam, then that shear force will interfere with the bending moment. And the code is suggesting us to reduce the design bending moment. So whatever the bending moment that we are getting, let's say MD is the bending moment that we are getting from the formula, we need to reduce it by a factor of beta times MD minus FJD, MFD. Okay. So this is the formula that is given in the code for the plastic and compact section. Okay. Again, this should be limited to 1.2 ZeFi by gamma mo. And for the semi-compact sections, it is governed by the elastic section modulus, that is Ze times of Fi by gamma mo. Okay. What is MD? MD is nothing but plastic design moment of the whole section. Okay. Disregarding the high shear force effect. Okay. And whatever that MD we are getting, we need to reduce it by a factor of beta times of MD minus MFD. Okay, what is MFD? Plastic design strength of the area cross section excluding shear area. Okay, considering the partial safety factor. So, what the code is saying that whenever there will be high shear force, my web will be ineffective in taking that moment. Okay, because my web is busy taking that high shear. So, whatever the total moment that we are getting, disregarding the high shear, okay, we need to subtract the plastic design strength of the cross section excluding the shear area. Okay, and we need to reduce that moment by a factor called beta, which is the moment reduction factor, and which is given by this formula. Okay, so this is also shown with the help of a interaction between moment and shear diagram. So here you can see the graph between V and M, that is shear force and moment. As you can see that beyond 0.5 times of VP at around zero point 0.6, you can see that my design moment is getting reduced. Okay, So this is the envelope that defines the maximum shear and moment that can exist simultaneously. In the next lecture, we are going to take a numerical example and we are going to perform manual calculations and design that beam, and we will verify those results using Statgo software. So stay tuned. Thanks for watching. Bye for now.